Today's class, we are going to discuss the applications of YDSE and interference in thin films and diffraction. Okay, so that tomorrow will be numericals on YDSE and numericals on thin films and polarization. Okay, mostly by tomorrow we'll complete the synopsis. Okay, now is it fine? Is it
Yes, sir.
fine? Okay, by tomorrow we'll complete the synopsis. Tomorrow is Thursday. Thursday means Friday and Saturday we'll do the numericals on this wave optics only. Okay, na?
Okay, sir.
Okay, okay, that is our plan. Okay, fine. Firstly, in the YDSE, okay, we studied that we are having a source and we are having a double slit. Here it is S1 and S2. Okay, width between the two slits, it is D. We consider this as small d. Whenever you are studying or you are preparing, read as small d and capital D. At a distance, capital D, we are having a screen. Screen is placed or photographic plate. Okay, fine. Now, the thing it is that okay, now here it is, whenever the light rays passes in between the slit, then the light ray will be undeviated. This is called as central fringe. And thereafter, the light rays will get diffracted, and then it will be superposed. Suppose let us consider this point as P, that is the nth bright fringe. And the distance between central fringe and nth bright fringe. It is YN. Okay.
Okay, sir.
Okay, fine. That is YN. Okay, fine. Now, here it is that we got the expression as YN equal to capital D by small d times delta. If it is bright fringe means I'll write, delta equal to n lambda, because it is maximum intensity. Bright fringe means maximum intensity. Similarly, for dark fringe means delta equal to 2n minus 1 times lambda by 2. Okay, na? Now, my first application. Okay. Find fringe width between any two bright fringes. Okay, na? Fine. Now here I am considering always you can see these bright fringes will get in the order of even number, right? In the order of even number. Can I say? Okay. Suppose let us consider nth bright fringe. And n minus 4th bright fringe. I need to find this fringe width. This fringe width I need to find. Okay. Let us consider this one as yn and this one as yn minus 4. Okay. I need to find yn minus 4. Is it right? That is, yn means, since it is bright fringe, capital D by small d times n lambda. Capital D by small d times n lambda minus capital D by small d times n minus 4 times lambda. Okay, now?
Yes, sir.
Okay, fine. Now, you can see here, it is upon solving, we'll get as capital D by small d times 4 lambda. Capital
Yes,
D by
sir.
small d times 4 lambda. Okay, fine. So here, whenever they ask to find the distance between the two fringes, okay, suppose let us consider an example as 10th bright fringe and 6th bright fringe, that is n equal to 10, right? Okay, so I need to find y10 minus y6. y10 minus y6, that is nothing but capital D by small d times 10 lambda minus capital D by small d times 6 lambda.
Yes, sir.
Okay, that is our first application. Now, next one, it is second application. Okay, application 2. Here I need to find fringe width between any two dark fringes. Okay, whenever it is dark fringes, it is in the multiple of odd multiple, right?
Yes, sir. Odd multiple.
Odd multiple. Okay, so I will consider it as I'll consider it as 13th dark fringe and 5th dark fringe. Okay, na? I will consider this 13th dark fringe as y13 and 5th dark as y5. Okay, so y13 minus y5 I can write as capital D by small d, capital D by small d times 2n minus 1 into lambda. Since it is 13th dark, na, so that's why I'm keeping 2 into 13 minus 1. Okay, na?
Yes, sir.
Minus capital D by small d times 2 into 5 minus 1. Sorry, into lambda. Okay, that is, we'll get as capital D by small d times 25 lambda minus capital D by small d times 9 lambda. That is nothing but capital D by small d times 16 lambda. That is, I can write it as 16th bright fringe. Can I say
Sir, 16th or 88?
16? For bright fringe, yn is equal to capital D by small d into n lambda. Na?
Sir, isn't lambda by 2?
No. Oh, here lambda by 2, na? Right. Capital D by small d, 2n minus 1 into lambda by 2, na? Here it is, yes, right, lambda by 2. So by 2. So it will be eighth bright fringe. Eighth bright fringe. Capital D by small d times 8 lambda. That is y8. So it will be eighth bright fringe. Okay, na? Fine. Okay. Next one.
Yes, sir.
Third application, it is application 3. It is find fringe width between suppose 24th bright fringe and 7th dark fringe. 7th dark fringe. Okay. So I will consider Y24. Since it is bright fringe, I can write as capital D by small d times 24 lambda and Y7, 7th dark fringe. So capital D by small d times 2 into 7 minus 1 times lambda by 2. Okay,
Yes, sir.
Okay, fine. So we can say that Y24, yeah, Y24 minus Y7, I can write as capital D by small d times 24 lambda minus 13 lambda by 2. 13 lambda by 2. Okay, na? So it will be 48 minus 13, approximately
Sir, 35.
48 minus 13, 35 lambda by 2. Okay. That is, I can say it is 18th dark fringe. Right? 2 into 18, 36 minus 1. Right?
Yes, sir.
Okay. That is from 18th dark fringe means Y18 dark, Y18D minus center. Right?
Yes, sir.
Okay, fine. So in these three applications, we are finding the fringe width. We found the fringe width. Now, application 4. Application 4. Okay, application 4, it is application 4, it is that I perform the YDSE experiment. YDSE experiment in air or vacuum. In air or vacuum. I got the fringe width as Yn is equal to capital D by small d times delta. Okay, fine. Either you can consider the constructive interference or destructive interference. Either you can consider the constructive interference or destructive interference. Here I am considering the constructive interference that corresponds to the bright fringes. Okay, that is yn is equal to capital D by small d times n lambda. Okay. Now, the same experiment I have done in an medium. In a medium, having a refractive index as mu. Then I want to find whether the fringe width is less than the previous fringe width, or it will be greater, or it will be equal. Okay. If the same experiment is placed in a medium, then what will be the fringe width? Okay, now is it fine?
Yes, sir.
Okay, fine. Now see here, whenever we did the experiment, capital D, it is the distance between slit and screen. Small d, it is the distance between slits.
Yes, sir.
Lambda is wavelength of light. So
Yes, sir.
if you done the experiment in air or medium, distance between slits and distance between slit and screen will not changes.
Yes, sir.
So I can say that capital D, comma small d, comma n will be constants. The only variable quantity it is wavelength. Whenever it is placed in a medium, it will be changes. Right? We know that by definition, refractive index is equal to C by V. Can I say?
Yes, sir.
Okay. Speed of light means frequency times wavelength, that is in air, by frequency times frequency of the particle does not changes. Whenever the
Yes,
light
sir.
ray changes from air to medium, frequency remains constant now.
Yes, sir.
So I can say that mu is equal to lambda air by lambda medium. Here mu is equal to lambda air by lambda medium. Lambda air means whenever I perform the experiment in air, I have the wavelength of light ray. Light wave is lambda. Wavelength of medium I'll consider as lambda dash. So wavelength of the light wave in medium will be lambda by mu. So yn dash equal to capital D by small d times n into lambda dash. That is nothing but n times lambda by mu. So I can say that yn dash is equal to yn by mu. Okay, now. Is it
Yes,
fine?
sir.
Okay, now. Now from this, since always mu will be
Greater than 1.
medium means we'll have greater than 1.
Yes, sir.
So always I can say that yn dash will be less than yn. Right?
Yes, sir.
So that is this one. Yn dash will be less than yn. That means I can say that whenever we repeat the experiment from air to medium, fringe width will be decreases. will be decreases. Okay, now fine. Is it fine?
Yes, sir.
I think next application. You can see we are having the fringe width as yn is equal to capital D by small d times lambda, that is delta. For dark fringes means 2n minus 1 to lambda by 2. For bright fringes means n lambda, right? Okay, na? Okay, fine. Now, from this expression, I can say that the fringe width is directly proportional to the distance between slit and screen. Okay.
Yes, sir.
That means as the distance between slit and screen D decreases, what happens to the yn?
Sir also decreases.
That means fringes will become closer or nearer.
Yes, sir.
Generally in the textbooks, they will write the terms like closer or nearer. Fringe width will becomes closer, or we can say nearer,
Yes, sir.
and vice versa. Okay. Yn is inversely proportional to D. Here, as distance between the slits decreases, Yn will be increases.
Yes, sir.
Okay, na? Yn will be increases. Here I am considering that D is constant. We are not changing the distance between slit and screen. Here small d is constant. Okay.
Yes, sir.
Fine. This is first result, second result, and then third result. Either for dark fringes or bright fringes, Yn is proportional to lambda. Yn
Yes,
is
sir, for all.
proportional to lambda, where lambda is the wavelength of the light rays, right?
Yes, sir.
Now, I will consider the two light rays. First light ray, it is visible light. Visible light means it will have the range of wavelength from 4000 to 7000 angstrom.
Yes,
Okay.
sir.
Okay, fine. Next, second, it is, suppose if I consider microwaves. Microwaves. Okay, microwaves will have a wavelength. Okay, microwaves will have a wavelength which is in the order of 10 power minus 3 meters to 10 power minus 7 meter. Hello? Microwave.
Yes, sir. Microwave. Yes, sir.
Okay, it is less wavelength. Now, here it is that lambda must be much more small than the distance between the slits. Why? Because why lambda must be much more small means, let me go to diagram.
Sir, in proof we done.
Huh?
Sir, in proof, yesterday we done that lambda should be less than
you know now.
D.
Okay, because in order for light to pass, the lambda must be very small. The distance between the slits means it is in the order of centimeters or it is in the order of millimeters. If I consider microwaves, then YDSE will not be possible. That is only this is only the condition on the YDSE. And the light rays must be coherent waves. The light rays must be coherent waves. So
Yes, sir.
in order to have this one, what I'm consider that it is, what I will consider it is, I'll consider as suppose X-rays. Okay, na? X-rays.
Yes, sir.
It is in the order of 10 power minus 9 angstroms. 10 power minus 9 meter.
Sir, can we take gamma rays?
You can take gamma, anything. No problem. Suppose gamma, okay, okay. 10 power minus 9 meter means approximately 0.1 angstrom.
Yes, sir.
Now, let us consider the wavelength of visible light is lambda 1. So, I will consider the fringe width as y1. K into lambda 1. Now, the wavelength of gamma rays, I will consider as lambda 2. That is y2 equal to k times lambda 2. Now, we need to explain whether y1 is greater than y2 or y1 is less than y2. Which value? Wavelength is decreased or increased?
Sir, wavelength is decreased.
Wavelength is decreased. So we can say that fringe width is decreased.
Yes, sir.
Can I say? Okay. That is this thing. Now, with respect to these, observe now carefully. Okay. I'll show the diagram. As the distance between the slits decreases, what happens to intensity? What happens to intensity? As distance decreases, what happens? Fringe width will be increases. Hello?
Yes, sir.
As the distance between the slits decreases, DEC, fringe width will be increases. Right?
Yes, sir.
As fringe width increases, that means distance between the fringes is increased. Right?
Yes, sir.
Okay. As the distance between the fringes increases means what happens to amplitude? What happens to the amplitude?
Sir, amplitude is also increased.
Amplitude increased. So since I know that intensity is proportional to square of the amplitude, na? Square of amplitude. So intensity will be increases. Okay, na?
Okay, sir.
Intensity will be increases. Okay, fine. Now, and vice versa. As distance between the slits increases, we can say that intensity will be decreases. Now, suppose as distance between the slit and screen decreases, what happens to intensity?
Sir, decreases.
Very good. Intensity will be decreases, right? Okay, fine. Intensity will be decreases. Okay, fine. These are the things. Next one, we are having that it is interference in thin films. These are the applications in the YDSE up to here. Okay, you can see here. These are the applications.
Okay.
Okay. Okay. Next one it is interference in thin films. In thin films. Okay, fine. Now, suppose, firstly, I will consider that I am having a source. I am having a source. Here, I am having a double slit. Okay. Here, I am having a double slit. And here, I am having a screen. I am having a screen, suppose. Likewise, beforely, we are having the distance between slit and screen is capital. And the distance between the slits is small d. Okay. Distance between the slits is small d. Now, in between the slit and screen, I am having a mica sheet. I am having a mica sheet whose thickness is T. Whose thickness is T. Okay. And this mica sheet is having a refractive index mu. Is having a refractive index mu. Now, in this case, I need to find the fringe width. What is the condition for the fringe width? Okay. Is it fine? Or shall I repeat the situation?
Sir, can you once again repeat?
Firstly, we are having a coherent source and double slit S1 and S2. Such that
Yes, sir. And then
small d is the width between the slits. At a distance capital D, we are having the screen is placed or photographic plate.
okay.
In between slit and screen, we are having a mica sheet having an thickness as T and a refractive index as mu. Refractive index as mu. Okay. Fine. Is it okay?
Yes, sir.
Now, likewise before, we can say that it is whenever the light rays passes through the slit. I am having a light ray which is passing through the slit like this. Another light ray which is incident on the slit S1 and slit S2. Okay, na? Fine. Soon after the incident on the slit, the light ray will get diffracted. The light ray will get diffracted. Okay, suppose let us consider here. Okay, fine. Okay, since here it is air medium, this is air. Light ray is moving from air medium to or rarer medium to denser medium, right? Okay, na? rarer medium to denser medium. When the light ray is moving from rarer medium to denser medium, I know that apparent depth, I think in ray optics, you might study the real depth and apparent depth, right? So that is mu times real depth,
Yes, sir.
and apparent shift will be apparent depth minus real depth. That is nothing but mu minus 1 times real depth. I will use this principle. So the apparent shift in the mica sheet will be mu minus 1 times t. Can I say? Okay, na?
Yes, sir.
Okay. Okay. After going through this one, these two light waves will superpose and will forms the interference pattern.
Yes, sir.
Okay. Now here it is at each surface. The light ray will have refraction and as well as reflection. Like this. Okay. The total phase difference between reflected wave and refracted wave. This total phase difference. What will be this total phase difference? This phase difference between reflected wave and refracted wave.
Sir,
What will
path
be
difference is
180. See this total now. So 180 degrees. So firstly, I'm having a path difference that is mu minus 1 into t.
Yes, sir.
Okay. And I'm having an additional path difference due to the phase difference. Okay, na? Okay. Here I'm having a phase difference. Here I'm having a phase difference of 180 degrees. That is nothing but pi radian. When phi equal to pi, what will be the value of delta?
Sir.
What will be the value of delta? What is the relation between phi and pi? Sorry, phi and delta.
Sir.